Okay, so today we'll be talking about statics and the information about it. Statics falls under mechanics. There's three types of mechanics. There's one for rigid bodies, one for deformable bodies, and one for fluids. Under rigid bodies is where statics falls. There's two under rigid bodies. Statics is for bodies at rest or at constant velocity, and dynamics is for bodies experiencing acceleration. Under deformable bodies, there's solid mechanics, and under fluids, there's fluid mechanics and gas mechanics. Some examples in real life where static mechanics falls under is, for example, like a bridge. In a bridge, you have to make sure the forces in it are all balanced in order for the bridge not to fall or break. And in a sign being held up, kind of like a for sale sign, you have to make sure all the tensions and all the forces in it equal zero so that the sign doesn't fall. So for our problem, we have this weight hanging off two cords from the ceiling. We are given D, and we're given the length of AB and the weight. So the way we used to solve this is the law of cosines, where we have, if our triangle, if we have this triangle, and we have this angle, and we're trying to find these angles, we can use the sides to figure out the length, the angle, the degree of the angles. So we have a squared equals b squared plus c squared minus 2bc cosine of a. And we can arrange this for any angle or any side. So we flip our triangle around to better meet this one. We have angle B on this side, angle A on this side, and angle C on this side. This would be the length of AB. This side would be length of AC, and this would be D. So if we use this equation to find angle A, which is theta, which is what we're looking for, we have the length of AC squared equals to the length of D squared plus the length of AB squared minus 2 length of D length of AB cosine A. Then we can rearrange this equation to find just angle A. So we have LAC squared minus D squared minus length of AB squared equals negative 2D length of AB cosine A. Then we divide over this negative 2D length of AB, and then we can take the inverse of cosine of this whole side in order to get just angle A. Another thing we have to solve for in this equation is the tensions in this string, and this string. Okay, so in this tension, the length of AB, there's a y component and an x component, and in this one, there's a x component and a y component as well. Since this one is just straight down, there just has a y component, which is negative. So if we draw a free body diagram, we have this point B, where all the tensions meet. And if we separate this into x and y components in order to get two equations to solve for both tensions, we have this positive x component, which is the tension. If we name this tension 1, tension 2, and tension 3, we have this tension 2x component, and on this negative side you have tension 1x component. Down here you have tension 3, and up here you have the y components of both tension 1 and tension 2 added together. From here you can make two equations in order to solve for the tensions. Since this weight is not moving, that means that our mass and acceleration, which is force, is 0. That means we can equal both sides. So this x component should be 0 since it's not moving side to side, and this y component added together should be 0 since it's not moving neither up or down. So we have tension 2x is equal to tension 1x. And then we have this tension 3 is equal to tension 1 plus tension 2. This third tension is equal to the weight while this x component of tension 2 is equal to tension 2 cosine of this angle, C, and then the y component is equal to tension 2 sine of that same angle, C. Same goes for this one. The tension 1 x component is equal to tension 1 cosine of the angle A, which is theta, what we're looking for. And then this y component is equal to tension 1 sine of A, or theta. That way we can use those to plug into this equation. So we have tension 1 cosine A is equal to tension 2 cosine C. And then we have this weight equal to tension 1 sine A plus tension 2 sine C. And if we can use this equation to solve for one tension. So we have tension 1, if we divide cosine A on this side, is equal to T2 cosine C divided by cosine A. There we can use that to plug it into here and solve for the other tension. We have weight is equal to T2 cosine C divided by cosine A. That's plugged in for T1. Sine of A plus tension 2 sine C. Since sine over cosine is tangent, we can use that to take out this and plug in tangent. So tension 2 cosine C times tangent of A plus tension 2 sine of C. Using that, you can pull out tension 2 from this side of the equation, leaving us with weight equals tension 2 cosine C tan A plus sine C. That way you can divide this part divided by that part. Equals second tension. Since we found our angles using the law of cosines, we can plug in our angles to find tension 2, and then we can plug in tension 2 to this equation to find tension 1. Now we're going to speak on describing our script. First, we start off by extracting the certain values that we are given from an Excel file. We load that in by using the function xlsread. Then we extract each individual value. So in the first column, they're going to give us D, which is the length of D, W, which is the weight, and then the length of AB, and we use D, W, and LAB as the variables to store those in. And we're going to have matrices which hold those values. Then we're going to use the find function to see if in any of those matrices, in any of those variables, we have any negative values stored, which would be a value less than 0. Then we're going to find the size of those matrices to be able to use that the size in our for loops. And we're also going to use the size of the original matrices to be able to compare those both. Then we're going to use the isEmpty function to find if any of those values contain a negative value. Now for our second part, we're going to have an if loop and an if and else statement and a while loop to check and display if we have any negative values and see what we want to do with them. So we're going to display that we're talking about the D value, and we're going to see if there are any negative values. Then we want to start a counter to identify that location, and we have the condition that as long as we have a negative value, which this variable means is the size of the negative values. So if we have more than one negative value, we want it to print out the negative value and the location of that value, and then it's just going to let us know that we're going to correct those negative values by using the absolute value of the one that was given. And we're just going to keep running this while loop as long as we still have a size of RDF which is greater than 0. And then if we don't have any negative values, we will display that there isn't any negative values, and we will move on to the third part. And for this one, we're going to talk about the W values, and we're going to do the same thing. that if there are negative values, we're going to run this while loop. We're going to start a counter to be able to have that location. And then we're going to display the W negative values and their locations. And then we're going to let the user know that we are correcting negative values by using the absolute value of that value to make sure that that's not the case. And then if we don't have any negative values in any of the tensions or the weight, then we're going to say that we don't have negative values found. Right here, we're going to focus on the length of AB. So if our length of AB is 0, if there are negative values, then we're going to start a counter as we did previously, and we're going to print the value, the negative value, and we're going to say the location. And we're just going to let the user know that we are correcting those values by using the absolute value. And we're using here to go down of the values. So if we have more than one negative value, we're going to show each one, and we're going to display it until we have no negative values stored. For loop, we're making sure that we have no values of LAB that are greater than D. So we're going to use the size of the original D matrix to make sure that to go through and run and check each value. So we're going to run the while loop until we check all values, and we're going to compare LAB to D. And if LAB is greater than D, then we're going to let the user know by issuing a warning, and we're going to ask the user to please enter a value less than what we have stored as D. And then the user is going to input that, and then we're going to use a while loop to make sure that that value the user inputted is not a negative value. And we're going to keep asking the user if the value is negative, and if it's not, we're going to end the for loop. Now right here we have our conversions. We're going to convert our LAB values are given to us as feet, and we're going to convert it to meters. And our weight values, they're given to us as pounds, and we're going to convert it to newtons. And then right here, we're going to use this for loop to generate a metrics for the thetas and the tensions. So we're going to go through our D values. We're going to pull out specific D values, and then we're going to go through our length of AB values and our weight values to be able to plug those into our function down here and find theta. So we're going to find the minimum that we can have LAC to LBC to be, and as we spoke about that earlier, the minimum that we can have that to be is the length of AB. And then the maximum that we can have it to be is if we use it as a hypotenuse. So we're going to solve for the hypotenuse right here as if it was a hypotenuse. And then we're going to create the values, a range of values that can possibly be the LBC. So it's going to be from the minimum to the maximum, and we're going to create 1,000 values. We created 1,000 values because we figured that when it plotted it, the graph came out a little choppy. So we used 1,000 so that it can be more smoothly. And then we're going to print out the length of AB and the length of D. So right here, we're using this for loop to run each value through our function. And then when we call on our function, we have this right here. And then right here, we're figuring out for the part that's going to be divided by W when we use the law of cosines. And then we have this inverse. We use an A cosine D that's the function to use when you're trying to find the inverse of cosine. And we're plugging for, which is that second, that part that you're going to divide by W. And then we're going to use this if loop. And we're going to find these tensions down here by dividing the weight times the inverse of cosine. And right here, down here is when we're going to print out all the values. So since we don't want 1,000 values printed out, what we did was that we rounded the values of theta, and then we chose a constant of 5. And if that theta value is divisible by 5, then we're using this if loop to print it. And if it is not, then we don't print it out so that we'll have a more limited amount of values printed. This next portion, we're trying to figure out a flexible range to be able to set up for the y values and for the x values, because we will be plotting it soon. So we're going to plot each every time we have the for loop runs, we're going to plot a graph, and we're going to plot the length of BC on the versus the tension of AB, and then the length of BC versus the tension of BC. And we're going to use the x minimum and x maximum and the y minimum and y maximum that were found previously. We're going to name it and then do the legend and the x label and the y label. And then next part, we're going to show a graph that shows all the tensions. So we're going to find the x and y maximums and minimums, and then we're going to plot the final graph using this for loop for every value of tension. We're going to plot the graph, and then we're going to do the title and the y and x label.